Does anybody, before we start, does anyone have any questions that you want to talk through before we get into this next bit?
Number 8 on the assignment in the worksheet.
What's it say?
That voltage would be 14 dB less than 19 volts.
14 dB less than 19 volts. So it would be, you need the voltage ratio for negative 14 dB. It's the first thing you need, right? So I would do 10 to the power of negative 14 divided by 20, and then multiply that by, how many volts did we start with? Did it say? 19 or something? So times 19 volts. Right? Because you want to, when I say something like what value would be this many dB more than this other value, right? You need to find the ratio for that dB difference. And this dB, so if it's negative 14 dB, then what is the voltage ratio for negative 14 dB? And that gets you a magic number. And you can multiply that magic number by any voltage, and you will get a voltage that is that many dB more or less, right? So jot that down, and then you can see if you can get that answer. I don't want to give it to you yet, and then we'll when we do the review, we can cover it. Okay, but that's, chase it down this direction, and you'll get somewhere. Whoops. What else? All right. Well, let's do this part then. So you remember that one time when I told you that decibels can't be used to communicate any actual value?
Yep.
Well, I wasn't being entirely truthful there. It is true that decibels, pure decibels, are not an absolute value. Okay, they cannot represent a real value. They can only represent the difference between two values. Okay. However, and a significant weakness and a reason why they cannot be used to show an actual value is that they are an abbreviation by their very nature. So a single number in decibels could actually represent multiple actual values all at the same time, right? So because they're collapsing these big ranges into small range. However, you can use decibels to approximate actual values if you can agree on one side of that equation as a constant. So if decibels always just tell you the difference between two things, if one of those two things could be some sort of mutually agreed upon constant value, then your decibel value represents a difference more or less than this known constant, this known thing. And then you could start talking about something very close to actual values. But keeping in mind that a single decibel value, even in that context, would represent, in reality, multiple real values, okay? So this is what are called reference levels. So in the professional audio community, we have agreed on certain reference levels. And this is just to some extent, there's a reason for each of these, but in some cases it's not. It's just fairly arbitrary. And I can't always explain to you why. Okay, it's just one of those things that you just have to be okay with. You just have to say, okay, fine, I will agree that that is a thing. Because if you don't agree that that's a thing, then you don't get to do sound for your profession, right? Because this is just this thing that, everybody who does sound for their profession, we have mutually agreed that we will agree with on this, okay? So one of these reference levels is called dB SPL. So anytime you see dB and then some combination of one or more letters after it, those letters that come after the dB are referring to some sort of reference level. And when you see SPL after your dB, that means sound pressure level. So decibels relative to sound pressure level. And the mutually agreed upon constant here is what's called the threshold of hearing. So there's been research done on kind of the range of human hearing as far as volume perception goes. And generally, they find that the threshold of hearing, being like the quietest thing that we can ever hear, is something around 20 micropascals worth of pressure, right? Because it's the pressure that creates the amplitude of the wave, okay? And amplitude in the air corresponds to loudness. So 20 micropascals is the quietest thing that we can hear. And so we're going to call that 0 dB SPL. Okay, so when you see 0 dB SPL, that is standing in for this actual pressure level of 20 micropascals. Now, the whole point here is that you don't ever really want to have to worry about the actual pressure values, okay, because it's a massive range, okay? You could do the math on it and start figuring out when we say things like 120 dB SPL, you could figure out how many pascals that would be, but it's not particularly important because it's a big, huge number that is not really meaningful to us. But being able to collapse this down into a smaller range using decibels is very meaningful to us. So if we can just agree as a group in this room and as a small subset of the larger world of professional sound people, that 0 dB is going to equal 20 micropascals. If we can just agree on that, then we can start using this value, this unit of measurement of dB SPL, to represent actual loudness levels. So if 0 dB SPL is the threshold of hearing, usually around 120 dB SPL is what's called the threshold of pain. And this is where the sound level is getting so high, the pressure level, that it can actually cause you physical pain in your ears. Some of you may have experienced that, right? That's not a good place to be, as we'll discuss on Monday. But you can certainly go higher than that, right? So there's the threshold of pain, but then there's even higher thresholds of like the threshold of blood or something like that. I don't know if that's what you call it, but I mean, you
like event horizon shit right there.
like you can actually, you know, rupture your eardrums with levels higher than that. But you definitely don't want to do that. What's interesting about dBSPL is that because we're talking about a pressure range here, and inverse square law applies, which is that 6 and 20 rule for inverse square law, which is you double the distance away from the sound, you lose 6 dB. You multiply the distance by 10, and you lose 20 dB. Conversely, if you divide the distance in half, in other words, get half as closer to the sound, you gain 6 dB. If you divide your distance by 10 and get closer, you will gain 20 dB. There's an interesting thing here about the way we perceive this, and this is important to understand. Because it turns out that we don't perceive every frequency the same way. So it's when we say that, 0 dB SPL is the threshold of hearing, that's true, but only for a certain frequency. There would be other frequencies where your threshold of hearing would be different. What this graph is attempting to show is the sensitivity of our hearing per frequency compared to various loudness levels. It's called the Fletcher-Munson equal loudness contours. Okay, so some researchers, a guy named Fletcher, a guy named Munson, did some work and some research, and they, used human subjects and played sound into their ears and tried to figure out, when they could start hearing it. And what they found out was that we are far less sensitive to low frequencies than we are high frequencies. So what this graph is attempting to show us, and this is, by the way, one of the most widely misunderstood graphs in all of sound. So I will attempt to demystify it for you. So it uses a reference point, okay, which is here, 1 kilohertz. And it says for a given pressure level, so for example, let's say, whoops, come back. There we go. So let's say for 40 dB SPL, which represents some sort of actual pressure level now compared to 20 micropascals, there would be, 1 kilohertz would be 40 dB SPL. However, for 100 hertz to sound as loud as 1 kilohertz sounds at 40 dB SPL, 100 hertz has to have, in reality, a higher pressure. So 100 hertz would have to be almost 60 dB SPL in order for it to sound as loud as 1,000 hertz sounds. Okay, so it has to be almost 20 dB louder than 1,000 hertz. So we are 20 dB less sensitive to 100 hertz than we are 1,000 hertz. Another thing that's sort of interesting about this is the reason we have multiple curvy blue lines here is that the sensitivity differences are variable depending on loudness. So as things get quieter, the sensitivity changes get more dramatic. So if we look now at 1 kilohertz at 10 dB SPL, now in order for 100 hertz to sound just as loud, it has to be 30 dB louder. Okay? However, when we get to higher levels, so now we look, here's 1 kilohertz at 90 dB SPL, 100 hertz only has to be 10 dB louder than it in order for it to sound the same level. Okay, so our sensitivity is different. Think about this as in terms of frequency response. The frequency response of our hearing is not flat. We do not hear every frequency equally. We don't. They proved it. But what's even more interesting is that the frequency response of our hearing changes depending on loudness. So it's this incredibly fluid thing. What does this mean in real life why do I care issues? Well, for you who in this class we're talking about designing sound systems, if you know this, you know that human beings are less sensitive to low frequencies than they are to high frequencies. If you want your sound to sound flat, like if you want your audience to hear all the frequencies equally, you now know that you need to deliver the frequencies to the audience not equal. You know that you have to have the low frequencies much louder in order for them to sound at the same level as the mid frequencies. You also know that the sort of mid to high frequencies, you look here in this sort of 1 to 4K range, we're more sensitive to those than we are to 1K. Now, why is that, do you think? Why are we so sensitive to that couple of octave range?
Human voice range.
Yeah. So those frequencies, about 2K to 4K, are the frequencies that contribute most to intelligibility of speech. In other words, our ability to understand the words that you're hearing. That intelligibility, which is all the consonants, the T's, the P's, and all that kind of stuff that helps us understand where words begin and end, that information is contained mostly in that 2 to 4 kilohertz range. And so our hearing system is naturally more sensitive to those frequencies because our hearing system's primary job is to facilitate communication. Now, you could do the math and figure out why this is, because if you think about what is the depth of your ear canal, for example, you could measure that and do resonance math on that. And you would find that the fundamental resonant frequencies of the various chambers inside your ear happen to coincide with these frequency ranges. So
does that mean that human speech evolved to be in the frequency range that we pick up best, or that we pick up best the range that is?
Yeah, I mean, deep thoughts. I don't know, but there's a clear connection though right? There's a clear connection to the sensitivity of our hearing and speech intelligibility. So we are most sensitive to the frequencies that contribute most to our ability to understand each other, okay? And when you start, losing your hearing and you start going to audiologists to kind of help you out with that, that's the stuff they're going to try to tackle first. They're going to give you a hearing test, and they're going to try to figure out what they can do, what sort of hearing aids and things they can give you to sort out this frequency range first, that 2 to 4 kilohertz, because that's the thing that's causing you to really frustrate all the people you live with, because they talk to you all the time and you can't understand what they're saying. And so the hearing aids are trying to tackle that frequency range first. They can get that sorted out, then your quality of life will improve quite a bit, because you can now understand what people are saying to you. Whether or not you can listen to your favorite music and have it sound the same anymore is less important. Okay. So this is something really important to understand. Our sensitivity to various frequencies changes according to frequency, and it also changes according to loudness. So the frequency response of our hearing flattens out as the sound gets louder and gets dramatically more or less even as the sound gets quieter. So that has some other implications. Implications on how we might measure loudness. So think about in terms of how loud is my show? Or how loud is the party across the street that the neighbors are complaining about? And how might we enforce some sort of a noise ordinance in a city? Well, if you understand that loudness and perception of loudness is not cut and dry, right? It's a variable thing depending on the overall loudness, depending on the frequencies that are being delivered. It gets a little complicated. So you can get devices that measure loudness, right? They're called SPL meters, sound pressure level meters. It's got a little microphone on it that you calibrate, and there's a little chip in there that is able to measure the voltage coming in off that microphone, because the microphone just converts sound pressure into voltage. That's all it does. And so the little device can be programmed to say, hey, when you see this voltage, that represents this sound pressure level. Okay? But knowing that the microphone is hearing all the frequencies, right? And our perception of loudness is different per frequency. So when it says, oh, this sound is 80 dB SPL, what frequency is it talking about? I don't know. I don't know. Depends. So there's this thing called weighting curves. SPL weighting curves. If you've ever used an SPL meter, there's usually a button on it for weighting. And it'll usually say A or C, if you've ever seen that, A/C. Sometimes it'll give you a B as well. What this is this is essentially an EQ for your sound pressure level meter. Okay? So the A curve corresponds roughly to the frequency response of our hearing at low levels. Okay, so this blue line, that's how we hear things that are quiet. Okay? The green line, which is the B weighting, that's how we hear things that are kind of average level, just comfortable listening level, as David Moulton says. That's approximately the frequency response of our hearing. The C weighting, that's approximately the frequency response of our hearing for loud things. Things where you would probably maybe want to put earplugs in, or things that would feel uncomfortably loud to you. C weighting is approximately the frequency response of our hearing. So isn't that interesting? So think about all that time you've spent sometimes, EQing things and flattening things out, and you realize that maybe the goal isn't to deliver flat. So in order to sound flat, you have to deliver something that is very not flat, because this is the way we hear. Okay, that's how things sound to us. So when you're using your sound pressure level meter, you can dial in these different curves to correspond to the loudness level. So most SPL meters don't actually give you B. Most of them give you either A or C. The only time I've ever really seen B curve is on computer programs that do this. So like the app on my phone, has a B curve on it. The smart analysis software will let you plop in a B weighting curve.
And what is the B?
So B is this is approximately the frequency response of our hearing for just comfortable listening level type stuff. Okay. So what it basically means is if you don't have B and you're choosing between A or C, my rule of thumb is I use A for 90 dB SPL and below. So if it's less than 90 dB SPL, then I'll use the A weighting. If it's more than 90 dB SPL, I'll use the C weighting. Because what you want to know is, does this loudness, what is the level of this loudness as perceived by a human being, not as perceived by an electronic circuit. And so that's what the weighting curve can tell you. If you plop in A weighting when you're measuring something less than 90 dB SPL, then whatever number is shown up there is going to represent how loud on average a human being is going to feel like this sounds. Whereas if you don't put the weighting in, then it's going to measure those low frequencies with just the same priority as the high frequencies. And if those low frequencies are loud, it's going to say, well, this is super loud. But the human beings are not going to be hearing those low frequencies as loud as the circuit is.
So is the SPL meter, does its job basically like, how loud is this really?
Yeah. How loud is this? It's attempting to quantify it in some way.
Yeah, because like the sound of things is like a subjective kind of thing where like somebody else might perceive it in a different way. So this is a way of being like, okay, let's get in like the general.
Yeah. Well, so think about you are involved in creating city ordinances in some sort of municipality, and you now have to figure out, how do I enforce a noise ordinance? Okay, and enforce it in a way that can be consistently applied and fair and all of that. Well, I will tell you right now, the noise ordinance in Forsyth County is ridiculous. It's horribly written. It basically just says, if you are annoying someone with the noises that you make, you are in violation of the noise ordinance.
So any old person, like anybody?
Anybody, any level, any loudness. If
Doesn't
someone
matter.
is annoyed, you are violating the noise ordinance. That's basically what it says. But a better written noise ordinance would be something like, you will be found in violation of the noise ordinance if the noise that you are making registers more than 70 dB SPL A weighted at the location of the person complaining.
That would definitely keep a lot more people from complaining.
Right?
I don't know what the hell this is.
Okay.
Because I don't know the exact ordinance, but I want to look it up now. Because Universal Studios in Orlando is like, because Disney World is its own damn planet. So
Right.
They can do whatever they want, be open as late as they want. But Universal is like in the middle of like a town.
Right.
And so like the parks are never open after like 11 o'clock.
Right.
Because apparently like people screaming on rides and all the crap that's going on
Right.
there is like loud enough to be
Well,
in violation of their.
right, because some of this, remember that sound gets quieter with distance, right? So the distance has to be part of the noise ordinance as well. So you have to. So the way, if someone says, "Hey, my neighbor's too loud," then a noise ordinance that is written such the way that I described it would mean that, a police officer would come over to your house, stand at your window with an SPL meter, set it to A weighting, and measure for a
They
while.
actually do that?
Well,
They
if
should?
they should, if the ordinance is written. I mean, like I say, in Forsyth County, it's not written that way.
They're just like, if somebody complains,
Yeah.
you're in trouble.
Yeah. So, but you would have to, it wouldn't be the same. The police officer couldn't just sit outside of the house that's making all the noise and do
Yeah.
the measurement. They have to be at the spot of the person who's listening, because it'll be quieter there if that's further away.
Right.
And they have to dial in the correct weighting on the SPL meter, because if they do C weighting, then the meter is going to automatically register a louder level than what the human being would be perceiving, right? So the SPL meter might say, oh, well, you're at 85 dB, but in reality, that only sounds like 75 dB to the person complaining, right? And if the noise ordinance says more than 80 dB, then that difference between measuring C weighting or A weighting would be the difference of you're violating or you're not violating, okay? So that's just one example of this. But now you think about a lot of venues, performance venues have loudness rules for, particularly that bring in touring shows and stuff. They'll have in the policies of the venue the show shall not exceed this loudness level. But if it's written well, it'll say it shall not exceed this many dB SPL, A weighted or C weighted, whatever they say, at the mix position. Right? So that means if people are saying it's too loud, they will have the meter there, and if you do touring shows like that and have a venue that has that part, it would behoove you to have an SPL meter at the mix position that's always running, so you can see if you've ever exceeded that. But again, you have to have the weighting curve, you have to have the location, you have to have the response of the meter, because the meter can respond quickly or slowly. It could do like an average level over a few seconds, which is probably better than a short period of time. These are all kind of things you have to do. I did a show last spring where we got complaints over the loudness, and we had a guy that was in the audience that actually came in and was very upset about how loud the show was. It was Schoolhouse Rock. It was staged as a big rock and roll show. It was loud by design. But and the theater did not know how to respond to this person. I mean, they said all kinds of things that they should not have said. That were not helping them, right? And they finally got me involved and just asked me, hey, what's going on? And I said, you should have come to me first, because the first thing you need to know is I took measurements of the show before I left, knowing that this might be an issue. I took measurements, and I can tell you that the show never exceeds, I think it was like, it never exceeds 90 dB SPL anywhere at any time. And that's, for 90 dB I would have done C weighted. So I can tell you that's the case. And when we start thinking about what it takes, as we'll talk about on Monday, to actually damage your hearing, well, there are guidelines for loudness exposure over time that would be safe. And I said, based on the measurements I took when I was there, the last run through before opening, I can tell you that the loudness levels of the show are well within OSHA guidelines for safe loud noise exposure. Now, when I say that the theater was saying things that maybe were not very helpful, is they had people telling people, well, it's not going to damage your hearing. It's not loud enough. And I said, well, I don't think you can say that. There are lots of reasons why someone's hearing might get damaged that may or may not have anything to do with this show. What we can say is that we took measurements, and those measurements are within established guidelines for safe noise exposure. That's what we can say. But you can only say that if you've actually taken the measurements, and you've taken the measurements properly with the correct weighting curves dialed in, and understand how to interpret that data. So that's one example now of a reference level that we can use. So we can now use dBSPL to actually represent approximate real sound pressure levels, okay? Let's look at another one. dBV. dB with a big V. So dBV is a decibel level, reference level, relative to voltage. And we have somewhat arbitrarily decided that 0 dBV is going to equal 1 volt. dBV is usually used in consumer audio equipment, like the kind of stuff you would get at Best Buy, okay, that has RCA connections on it or something, right? So the specification sheets for all that are usually going to be listed in dBV. And the dBV is just, again, it's standing in for the actual voltage levels that come out of the audio outs of that thing. So the nominal operating level for consumer equipment is minus 10 dBV. What that means is when the meter hits unity, hits 0 or whatever, that's usually minus 10 dBV. And that minus 10 dBV corresponds with specific voltage, which is, I believe, 0.316 volts is minus 10 dBV, okay? We'll do the math on that a little bit later. Because it's voltage, which is a force, it follows the 6 and 20 rule. So you double the voltage, you go up 6 dB. You multiply the voltage by 10, you go up 20 dB. Okay? If you divide the voltage in half, you lose 6 dB. Divide the voltage by 10, you lose 20 dB. So you primarily see this in consumer level equipment, okay? So when you see something that says minus 10 dBV, for example, what that means is this voltage is 10 dB less than 1 volt. That's what that means. The V means relative to 1 volt. 10 dB, minus 10 dB relative to 1 volt is what the V means. That make sense? Okay. Here's another one, dBm. dB with a little m. The m stands for milliwatt. So this is dB relative to 1 milliwatt. So in this case, 0 dBm is equal to 1 milliwatt, or 0.001 watts. This is used primarily in wireless transmission. Okay, so you'll sometimes see like wireless mics that have transmitters on them specified in their transmitting power level, and that'll be specified either in actual milliwatts or sometimes dBm. Okay, this is also used in like Wi-Fi, Bluetooth. They're specified. Their transmit and receive levels are usually specified in dBm. So decibels relative to 1 milliwatt. So it's a certain amount more or less than 1 milliwatt. Okay. So that nominal level, which is sort of like when it's operating at its regular level, that varies depending on the application. Is different for Wi-Fi than it is for Bluetooth than it is for wireless mics, so on and so forth. But because this is power, watts are a power, they follow the 3 and 10 rule. So dBm follows 3 and 10 rule. You double the power, you go up 3 dBm. Multiply the power by 10, you go up 10 dBm. Okay, 3 and 10 rule. So anytime you see a little m next to a dB value, you know that dB value is a certain amount, that many dB more or less than 1 milliwatt. Okay? Here's another one, dBu. dB with a little u. So the little u stands for unloaded. And why unloaded? Well, in the professional audio world, we used, you know how you have to sort of worry about loudspeaker impedance when you're connecting an amplifier to a loudspeaker? There's like 8 ohm loudspeakers, 4 ohm loudspeakers, 16 ohm loudspeakers, and the impedance of the loudspeaker affects how much power the amplifier can drive into that loudspeaker. Well, we used to have to worry about that for every single interconnection in our entire system. So plugging a microphone in, plugging an EQ into your signal. I mean, you had to worry about the impedance, the input impedance of the thing you were connecting compared to the power output that the previous thing could put into that kind of a load. And it was called impedance matching, and it was this, you had to do it with every little connection point in your system, which was not a very fun thing to do. So somewhere along the way, we realized maybe we should not worry about that so much, and we could somehow standardize the input impedance of line level, low voltage stuff, or at least say that there is a standard, and then compare actual devices against that standard. If we could at least do that, then we wouldn't have to keep dealing with dBm for all of our interconnects and have to worry so much about impedance. So that's what the unloaded means. As dBu was, let's look at this from a voltage point of view instead of a power point of view. And the way we can look at it from a voltage point of view is by standardizing the input impedance. And that standard input impedance is 600 ohms. So what basically that means is that 1 milliwatt, that 0 dBm, if you put that up against a 600 ohm load, it dissipates 0.775 volts. Okay? So that's why 0 dBu is 0.775 volts. 0.775 volts is what you get out of a 1 milliwatt signal that's pushing up against a 600 ohm load. Okay? So, and you could do the math on that and figure that out if you wanted to. However, the important part you need to know is that 0 dBu equals 0.775 volts. You just need to memorize that, okay? plus 4 dBu is the nominal operating level. So dBu is used in professional audio equipment. Okay, so things that have XLR connections on them, is probably a good test of knowing, is this a professional piece of equipment or a consumer piece of equipment. If it's a professional piece of equipment, it's going to have XLR connections on it, at least a few. Okay, if it's consumer level equipment, it's going to have things like RCA or little 1/8" headphone jack connections on it. Okay, so if you see XLR connections on it, it's probably specified in dBu, and its nominal operating level is plus 4 dBu. And you could figure it out. We'll do this in a moment. How many volts that plus 4 dBu would actually be. So, your mixing console, like this little guy here, if you look at the meter on the Mackie Big Knob here, it actually says 0 on the meter equals plus 4 dBu. So when the meter hits the 0 mark, that means that the signal is passing through this device at plus 4 dBu, which is a certain voltage. Okay? It's voltage, so it follows the 6 and 20 rule. Okay? Double the voltage, you go up 6 dB. Multiply the voltage by 10, you go up 20 dB. And inverse for dividing. Okay? Everybody with me?
Yeah, I guess the only thing I'm confused about is like what this means. Like, I guess from what I'm understanding, unloaded is without the complexity of milliwatts.
Without the complexity of impedance. So we're standardizing the impedance. We're standardizing the load of the input of the device. So that doesn't mean that the input on every piece of professional audio equipment is 600 ohms. It doesn't necessarily mean that, but it just means that that's the standard. Okay, and if we can, if we can agree on some starting point for dB, then we can start using it for an absolute level. If we can agree on some input impedance for line level devices, then we can stop worrying about impedance.
So this is kind of like the way that decibels in general just makes these concepts like easier to deal with.
Exactly.
Got it.
Okay. So that's all that's going on, is we're just saying, you know what, when we're dealing with low voltage stuff, things that happen before the power amplifier, let's just assume that the inputs of everything are very high impedance and the outputs of things are very low impedance. And if we can assume that, then we can stop worrying about it. Okay? And just talk about it in terms of dBu voltage. Okay? All right, so another one, dBW, dB with a big W. In this case, 0 dBW equals 1 watt. So if you see something that says 10 dBW, that means this power level is 10 dB more than 1 watt. dBW is not used a whole lot because once you get up to ranges more than 1 watt, at least in audio world of power amplifiers driving loudspeakers, you're usually not dealing with massive ranges. I mean, it's 1 watt to 10,000 watts is really about the biggest range we ever deal with, and that's doable, right? I mean, that's not a huge number from a mathematics point of view. And so there's less benefit to collapsing down to dB when you're dealing with those kind of power levels. But if you want to, you can, and if you see that in a spec sheet, that's what they're talking about. So it's power, so it's the 3 and 10 rule, okay? So you double the power, you go up 3 dBW, multiply that power by 10, you go up 10 dBW, okay?
So the general rule, power is 3 and 10, and force is 6 and 20?
Yeah.
Great.
Or basically everything is 6 and 20 except watts.
Great.
If it's watts, it's 3 and 10. Everything else, 6 and 20. Okay? Okay, so let's try some of these. So remember I said that the nominal operating level for DBV, or consumer level equipment, is minus 10 dBV. Remember that? I said that in like 3 or 4 slides ago. So what we want to know now is how many volts is that? Anybody remember what I said? No. Doesn't matter because we're going to figure it out right now. Okay, so if I were to express the definition of dBV mathematically, this is what it would be. So dBV equals 20 times the log of some variable, x, divided by 1 volt. That is the mathematical definition of dBV. So you with me there?
And X is the number that you're given.
Well, x would be the voltage, the actual voltage. Okay? So in this case, I already know the dB, right? I already know this. So if I solve for that, I'm going to do voltage ratio now, or force ratio, right? So in reality, what I would really want to do is say, if I want to get the actual voltage, it would be 10 to the power of minus 10 divided by 20 times the reference level. And what is the reference level? What is the reference level for dBV? 1, right? Times 1 volt. Okay? So to figure out how many volts is minus 10 dBV, we do 10 to the power of minus 10 divided by 20 times the reference level for dBV. And the reference level for dBV is 1 volt. So shall we try this? Yes, Jason, let's try it. So I'm going to say 10, and I want that to be a negative number, so I'm going to push this little button there. So negative 10, and I'm going to say divided by 20. I get negative 0.5, right? And I'm going to hit my 10 to the x button. And then I'm going to say times the reference level for dBV. And the reference level for dBV is? 1 volt. So times 1 equals 0.316 volts. So minus 10 dBV is 0.316 volts.
Yeah, I went, okay, 10, negative 10, times 20,
No, divided by 20.
divided by 20. Okay, negative 2.
No. Negative 10 divided by 20 should be negative 0.5. Okay, watch me do it. 10, negative 10, divided by 20. And I get negative 0.5. And then 10 to the x gives you 0.316 times the reference level of 1, and you get 0.316 volts. Now, yeah, I know, I didn't really have to do the times 1, but you need to get in the habit of that because it's not always times 1. Okay, you got to get in the habit of always multiplying those force ratios by the reference level, because if you always assume that it's 1, and then when it's not 1, you're going to get the wrong answer. Okay?
So, what did you put in for volts again? Okay, after you did negative 5, then what did you do?
The 10 to the x.
The x.
Yeah. 10 to the power of x.
So when you said the reference level for volts,
Reference level for dBV.
The reference level for dBV. In the slide, it said 0 dBV equals 1 volt. So
That's the reference level.
okay. So why is it 0 dBV equals?
Because it is.
1 volt? Okay, cool. I'm okay with that. I'm fine with that.
You just have to agree with that,
That's
or you don't,
actually a better answer than
or you
anything
don't
I
get to be a
said.
sound person.
That's fine.
Okay?
I'm okay with that. But I should just know that, so the reference level for dBU is the 0.775. Okay, that's fine.
It just is.
Okay.
Okay. All right. So how about this one? How many volts is plus 4 dBU? Okay, so this is basically the same problem again. We're just doing it in dBU now. So let's just write out these formulas really quick. The mathematical definition of dBU is 20 times the log of x divided by 0.775. Okay?
So all of these are going to be 20 log times x over the reference level?
All of them that are not watts.
Okay.
And then if it is watts, it's just
10 times the log of the variable divided by the reference
Oh,
level.
because this goes with the 10 and 3 and the 6 and 20?
Correct.
Okay.
So that's the mathematical definition of dBu. dBu equals 20 times the log of x divided by 0.775. Now, I already know the dBu, right? And by the way, x is a voltage in this case, right? Some number of volts.
Okay.
So I already know the dBu. And so if I solve for that, then of course it's 10 to the power of that dB divided by 20 times the reference level,
Which is
0.775. So in this case, for dB, I'm just going to put 4. So 10 to the power of 4 times 0.775 will give me the actual voltage level of plus 4 dBu. Shall we try that? Yeah. 10 to the power of 4.
But it was 4 divided by 20.
Yeah, sorry, 10 to the power of 4 divided by 20.
But you
Sorry, I said that wrong.
4 divided by 20 first, right?
Yeah.
Simplifies to 5.
Simplifies to 5. Okay. So let's just prove that. So 4 divided by 20 equals 0.2. 10 to the x, 1.58.
Wow. Yeah.
Right? Times the reference level, which is 0.775 volts. So remember, that number that we had, that 1.58489, that is the magic number. You multiply that number by any voltage level, and you will get a voltage value that is 4 dB more. And in this case, we're going to multiply it by 0.775, because 0.775 is the reference level for dBu. And I want to know how many volts is plus 4 dBu. So I'm looking for a value that is 4 dB more than 0.775. So I'm going to take that number I got, multiply it by 0.775, and I get 1.23 volts. That's another one that should go into your long-term memory.
You did the same thing that I did. It was like automatically like, oh, it's 5, but because it has to be
it's just
4.
reversed.
Yeah, it has to be the other way.
Yeah,
Because I mean, like normally you would divide by the bigger number.
right.
And I just noticed that too. That's weird that it's just like you have to divide by the smaller number or whatever the number is.
Right.
It could be a smaller number. It could be a bigger number.
Yep. So this is one of those things to memorize. 1.23 volts plus 4 dBu. Okay, that's nominal operating level for most of the equipment that you will use in your professional life. 1.23 volts. Here's another one. How many dBu is minus 10 dBV? Okay, so here we're going to convert from one abstraction to another abstraction. To do this, we have to convert it back to actual voltage first, and then we convert that voltage into a new decibel level. Okay, so we can't compare dBu and dBV directly because they correspond to different reference levels, right? So we can't just say that, well, 10 dBu is the same as minus 10 dBV, because it's not, because they have two different reference levels. So the first thing we need to do is find out how many volts is minus 10 dBV. We already did this. Remember what it was?
0.31.
0.316 volts,
Oh, I didn't put
right? The 6 is important
Okay.
in this case. Okay, so now that I know that, I just need to find out how many dBu is 0.316 volts. And remember, the mathematical definition of dBu is dBu equals 20 times the log of x divided by 0.775. So in this case, for x, I'm going to plug in 0.316.
Negative 7.79.
Let's try it. So I'm going to say 0.316 divided by 0.775 equals 0.408-ish. log times 20. Yeah, I got negative 7.79.
And when you do log, it's the log 10 or?
Mm-hmm, log 10.
And then-
So minus 10 dBV is equal to minus 7.8, basically, or 7.79 dBu. So you could say minus 7.79 dBu or minus 10 dBV, and you would be referring to the same voltage. Both of those things represent 0.316 volts.
How do you know when your answers need to go to 3 decimal places and when they only need to go to 2? Should you just put 3 to always be safe? Like, would you be wrong if you put more numbers?
I would say generally when you're dealing with, very small numbers, like when I say 1.23 volts, there's a difference between 1.2 and 1.3 that is somewhat significant. But when you get to really big numbers, it's less important, right? So the smaller the number, I would say, the more decimal places I would want to work with.
Okay.
Yes.
Yeah, technically the official thing is when there's questions or things, you just have the same amount. So if there's like a question that's like, calculate something of point where the question has 3 decimal places, then you have all your answers in 3 decimal places.
Generally, I say 2 decimal places for most of the things that we would do. And the exception to that is any of these like predefined reference levels that, like, if you just like look up in the textbook, what is plus 4 dBu, and they're going to say it's 1.23 volts. So there's to 2 places. But if you say what is minus 10 dB, they say 0.316. So in those cases where they're specifying it, as a certain number of decimal places, that you just memorize that. But generally, I would say stick to 2 decimal places for what we're doing. Because since most of what we're doing is dB, and dB is like such a mushy number, it's in reality the difference between 1 decimal place and others is very small, right? But the spec sheets will very often specify some of those really small voltages down to 3 decimal places. Okay, let's see what else we got here. How many dBm is 0 dBw? Okay, so remember, this is the same question as before. We're just doing it with watts now. Okay, we can't compare dBm directly to dBw because they have different reference levels, right? How many watts is 0 dBw?
One.
Yes. So 1 watt. So what I'm really asking is how many dBm is 1 watt? Right?
Yes.
Now the mathematical definition of dBm is dBm equals 10 times the log of x divided by 0.001. That's awful. Okay, there's your mathematical definition of dBm. So in this case, for x, I'm just going to plug in a 1. My 1 watt. So if I want to know how many dBm is 1 watt, I do 10 times the log of 1 watt divided by 0.001, because 0.001 watts is the reference level for dBm, right? Because 0 dBm is 0.001 watts. So let's try that. One divided by 0.001 equals 1,000. Log 10 times 10, 30.
Wait. What did I do?
So 0 dBw is equal to 30 dBm. Interestingly enough, that is one of the first problems we solved when we started talking about dB. I asked you how many dB is 0.001 watts. And we walked it back 3 decimal places, 3 factors of 10, and got 30 dB. It was the first bits of math we did last week. And here we are doing it again, with it hopefully being a bit more meaningful because it's now with a reference level. So 1 divided by 0.001 log times 10 gives you 30. What is the dB difference between plus 4 dBu and minus 10 dBV? What's significant about those levels?
Oh, there.
Yeah, they are both nominal operating levels for their respective subsets of sounddom. Okay, so plus 4 dBu is the nominal operating level for professional equipment, called professional line level, and minus 10 dBV is the nominal operating level for consumer level equipment, or consumer line level. Why is this important? Well, sometimes you are going to end up plugging consumer level equipment into professional level equipment. And it sure would be nice to know what would happen if you did that. And that's essentially what this thing tells us. So what is the dB difference between these two nominal operating levels? Well, these are two different reference levels. I can't compare them directly, right? What I need to do is convert them back down to their voltages and then find the dB difference between those two voltages. So how many volts is plus 4 dBu?
Oh, yeah, that.
1.23. I told you to memorize that, right?
Yes.
Anybody memorized it yet?
No.
No? Okay.
But I looked at it.
Minus 10 dBV.
Is 0.316.
Yeah, there you go. I got two voltages. How do I find the dB difference between two voltages?
Oh,
I have two voltages.
10 to the power of voltage divided by volt. No?
No.
Not the 20 log.
Yeah. 20 times the log of one voltage divided by the other. The 10 to the power of is if you already have dB.
Ratio,
If you already have dB and you need to get voltage. So we could use that to convert plus 4 dBu to 1.23 volts, for example.
Which one do you put on top?
Doesn't matter.
Doesn't matter. Okay, cool.
Whichever one you want. You're either going to get a positive number or a negative number, but it's going to represent the difference between these two things.
Got it.
Okay? So let's just say 1.23 divided by 0.316. Somebody want to do that?
11.8.
That sounds about right. 1.23 divided by 0.316 log 10 times 20, 11.8. So what does this tell us?
There's almost a 12 dB difference between
Yes.
professional and consumer.
Consumer level equipment is 12 dB quieter than professional level equipment. Why is that important to know? Well, think about this. Let's say you have, just make this very simple, 2 CD players that you're going to hook up to your sound system. One CD player is a professional CD player. The other one is a consumer CD player. So the professional one has XLR outputs on it. The consumer CD player has RCA outputs into it. And you're going to plug them into the same mixing console. You could play the same CD on both CD players, and the consumer one is going to come into the console 12 dB quieter than the professional one. And if you know that, then you know right out of the box before you ever even play a CD that you're going to have to turn the input gain up for that consumer level device. You're going to have to turn that input gain up by 12 dB in order for the CD to sound the same level as the same CD being played on the professional level CD player. Right? Because the consumer one just operates 12 dB quieter.
Is it just because the needs of it are not as demanding, or just because I feel like
It just is. Okay. I mean, there are probably some reasons, but they're not important
that's fine.
for our
I'm
purposes.
cool.
Okay. One of those reasons has to do with balanced versus unbalanced. You get a 6 dB boost by balancing the signal to begin with, and the other 6 dB is something else. But it's basically 12 dB difference, and that's something that's kind of important to know. Right? So usually you'll be working with professional mixing consoles. Anytime somebody hands you something that has an RCA output on it, you know that that thing is going to be 12 dB quieter than everything else in your system. And it's very easy to compensate for that. There are knobs that allow you to compensate for that. But you have to know that that's the case. Okay, here's another one. This is not a particularly practical question, but because because I don't really know why you would ever want to know how many dBm is a 300 watt amplifier, but you know, just for fun, how many dBm is a 300 watt amplifier? Well, remember, dBm equals 10 times the log of x divided by 0.001. Come back. And in this case, x would be 300, right? 10 times the log of 300 divided by 0.001. So 300 divided by 1 equals 300. Oh, no, sorry, 0.001. Whoops. 300 divided by 0.001. We get 300,000 log 10 times 10, 54.77 dBm. Did anyone else get that?
Yes.
Yes? Okay, good. It must be right.
Does it not seem right?
No, I just want to make sure. Sometimes I do it wrong. That's why we say it's not right until 3 people have the same answer. Okay. All right, so there you go. A 300 watt amplifier is 54.5-ish dBm. Again, not a particularly useful bit of information, but interesting. Okay. Okay, so now we've gotten through reference levels. I want to go back and talk about sound pressure level again for just a second. So here's what an interesting thing to understand about sound pressure level is, yes, it follows this thing called the 6 and 20 rule, right? And we know this about inverse square law and all of that. But sometimes it's easy for us to forget that dB is an approximation. It's not an actual thing. And what that means is when you start looking at things in decibel levels, the math is not linear. Okay? And what I mean by that is you can't just add decibel values together and get a linear result. In other words, if you have 2 sound sources that are both putting out 90 dB SPL, right? 2 loudspeakers. And this happens all the time, right? 2 loudspeakers, each loudspeaker is putting out 90 dB SPL. They do not sum together to create 180 dB SPL. If they did, everybody who had a home theater system would be deaf. Okay? Right?
Yeah, because the threshold of pain is 120.
Yeah. Okay? So if you think about this for more than 5 seconds, you realize that that would obviously not be true. 90 dB plus 90 dB SPL is not 180 dB SPL. Okay? In reality, what happens is, remember, this is pressure levels, right? And if you say 90 dB SPL plus 90 dB SPL, well, those 2 levels represent actual pressure values, right? And if you double the pressure value, normally you would get 6 dB, right? Because it's a 6 and 20 rule. So why am I saying that you'd only go up 3 dB?
Because 3 dB is double, right?
6 dB is double when you're dealing with pressure. So why am I saying only 3? Here's a little tip. Whenever I ask a question like that, the answer is almost always comb filtering. Yeah. So it's comb filtering is the reason. Okay? Yes, it should be 6. And in reality, for really, really low frequencies that have massive wavelengths, that would be 6. Okay? But for most sounds that you would listen to, it's really only going to be 3 because of the comb filtering. It's not going to allow it to sum perfectly. So you have 2 sound sources, you put them together, and together they create something that is only 3 dB louder than what they are doing individually. So it really is like 1 plus 1 equals 3. And that's very difficult to understand, but it's super important to understand because once the sound hits the air, your ability to manipulate it is very, very limited. Okay? So let's just say that you've set up your sound system and everything's hunky-dory and you've got your gain structure all lined up and this system is putting out every ounce of sound it's capable of doing. It is as loud as it is ever going to be. and it's not loud enough. Okay? You could call up your dealer and buy that entire sound system again and set it up in the same room right next to the first sound system, and you would only get 3 dB more sound. Right? You understand that? You just double the entire sound system, and you will only get 3 more dB. And that would be a little annoying for the person who had to write that check. Right?
Or the person that has to go install 2 sound systems.
To make a barely perceptible difference. Right?
Just enough perceptible.
Yeah. Okay. Another interesting phenomenon here is if there is more than 10 dB or more difference between 2 things making a sound, the quieter thing may as well not exist, because you will only perceive the level of the loudest thing. So you will only get any increase in level, even the smallest increase in level, if they are less than 10 dB apart from each other. They have to be less than 10 dB apart for them to even make a difference at all. Okay? So another example of this that is sort of fun to do. Anybody ever noticed the kind of makeup of a symphony orchestra, like the string section? How many violins are there compared to basses?
4 to 1.
It's a lot more, right? Okay. Why? I mean, these instruments have been around for hundreds of years. So over the hundreds of years, they've figured out that that's what you need. And that's what you need in order for it to sound equal, right? The sound,
Sound flat.
right. So, but why is that? Well, violins are quieter than basses, right? They're smaller. They move less air, okay? So, but why do we need so many more of them?
Because they don't just sum together.
Exactly. So let's just say, I don't know, let's say that one bass is going to deliver on average 80 dB SPL at 1 meter. Okay? I'm just making these numbers up. I don't know if this is actually true. And let's say that violin is going to give you something like 65 dB SPL at 1 meter. Okay? And that's kind of just on average. There's a 15 dB difference between them. Okay? So you've got one bass and one violin. And you can't hear the violin. So you say, all right, I need more violins. Well, so that would be one violin. So you could go hire another violin player. Now you have 2 violins. And how much louder are the violin section going to be now? 3 dB more. So now it's going to be 68 dB SPL. Still not as loud as the bass. So I need to get the violins louder. Hiring one more violin player is going to get you nowhere.
Because it doesn't double.
Right. You have to get at least 2 more violin players to make an even perceptible difference. Right? So now we have 4 violin players. And how many dB are we now?
71.
Now we're at 71 dB SPL. Still not as loud as the double bass. Okay? So I want to make a barely perceptible difference in the volume of the violin section. I have to hire 4 more violin players to make a barely perceptible difference. Okay? So now I'm at 8 violin players. And how many dB am I? 74 dB SPL. Still not as loud as the bass. Okay? If I want to make a barely perceptible difference, I have to hire 8 more violin players now. So now I'm at 16 violins. And we're at now 77 dB SPL. Still not as loud as the double bass. If I want to get as loud as the double bass, I now
32.
have to hire another 16 violin players. And now I'm at 32. And now I'm at 80 dB SPL. Now, in reality, there's not actually that big of a difference between violin and double bass. But there's probably closer to a 9 to 10 dB difference between them. Right? And that accounts for your sort of 4 to 1 approximate.
I want to see
Right, but so these numbers aren't necessarily practical, but the point I'm trying to get at is that once the sound hits the air, it behaves a lot differently than you assume it does. And your ability to manipulate it once it hits the air is severely limited. Okay? So you need to tackle the loudness problem before the sound hits the air. For example, what if we could just get the bass player to play a little bit quieter and the violin player to play a little louder, right? That would be a lot easier than hiring 32 more violin players, right? So same thing in your sound system. Rather than going and buying an entire second sound system, maybe you could just get a few, whatever your biggest loudspeakers are in the system, replace those with something more sensitive. Right? A loudspeaker, remember I said the sensitivity is, the 1 watt, 1 meter rating. How many dB SPL does it put out, 1 watt, 1 meter? Well, you could, instead of buying a whole other sound system, just buy another loudspeaker for your center cluster that can make more sound with 1 watt. And that would be a heck of a lot more efficient than buying an entire another sound system. Yes?
Close down to the source.
Yes, exactly. So your sound system, yes, your sound system has a fixed gain, right? And a microphone's picking up the thing. Well, if the thing itself could get 6 dB louder, like the person could sing 6 dB louder, or the instrument could play 6 dB louder, and your amplifier then amplifies it, your system amplifies that by its fixed amount, then suddenly you're getting the same increase in gain as you would get by having 3 sound systems in the room. Okay? So the further down the signal chain we get in our sound system, the harder it gets for us to manipulate it. Okay? That's the point I'm trying to make here. Okay. Now there's another thing we need to understand about loudness, and it's this concept of RMS, root mean square. I don't want to get into the math of that, but however, the thing you need to understand is given this graph of in this case volts, but it could be sound pressure level, whatever, you would call this, in this case, a 1 volt signal, because that's the value of the peak. However, if you consider what that would sound like to us when we listen to that, it only is at the 1 volt for a very, very small point in time, right? The rest of the time, it's less than 1 volt, right? Here, it's less than 1 volt. There, it's less than 1 volt. Less, right? Most of the time, it's less than 1 volt. And our hearing system hears the average of things, not the instant peaks of things, okay? And so if you actually just do the math, if you just average this wave out for this 1 volt wave, the average would be 0.637 volts. The RMS level, root mean square, is 0.707, and that corresponds to more or less what we would perceive, okay, and what we would hear. And what you would measure on a meter and stuff would be the RMS level. Now, what does that mean? This issue of RMS will crop up all over the place. But the part of it that I want you to understand is that whatever level your sound is, whether you're looking at it in voltage or watts or pressure or whatever, you will hear and perceive the RMS level, not the peak level. So when I say you need to deliver 100 dB SPL at the back row, that's RMS. You want the audience to hear and perceive 100 dB SPL. In order for them to hear 100 dB SPL, you need to be able to create more than that, right? Because they will perceive the average of the sound, or the RMS of the sound, not the peak. So the peak has to be much louder. This is called, this thing called a crest factor. So now you get into a complex sound that has lots of frequencies in it, and your RMS, or your average value, is, whoops, there we go. Sorry.
It's okay.
I'm just glad I didn't hit you with that. Okay, so here's your RMS level would be about here, but your peak would be here, right? So this difference between the peak level and the RMS level is called your crest factor. And the annoying thing about crest factor is that is sound you have to make that you don't get to hear. Okay? But you have to make it.
It's like overcompensating to get, or like compensating for what you need to get.
Yeah. So what we want to hear is this level. But in order to hear that level, we have to make this level.
That's so annoying.
Yeah. So this is called headroom. So you have to build into your system enough headroom to accommodate the crest factor, that difference between RMS and peak. Now that difference could be a little or it could be a lot. On average, I use the rule of thumb of about 6 dB. Okay? So I try to design my sound systems so that I'm capable of creating about 6 dB more sound than I really need. Because if you don't do that, then you're going to keep turning at the system, trying to get to that level you want. And if you didn't build the headroom in to accommodate for that crest factor, what's going to happen? It's going to be quieter than I expect, so I'm going to keep trying to get that level. I'm going to keep turning things up until I start clipping. And eventually, I'm just going to clip off all those peaks, which is, yeah, sounds amazing, right? In golden ears, right? How great does distortion sound? So good, right? It sounds really not great. But that's what happened. If you do not account for the crest factor in your system, then in order to get the level you need, it's going to just be distorted because you're going to clip all that off and it's just going to distort, okay? And yeah, you'll get that level, but it's going to sound awful. So those are your options. Either you get the volume and it sounds awful, or you don't get the level and it's just quiet, okay? But that's just an important thing to keep in mind. When we talk about perceived levels, we usually are talking about the RMS level. And the actual value you are producing to achieve that is higher, okay? And as I say, my rule of thumb is about 6 dB. So when we do the math, like how many watts is it going to take me to get this many dB at 10 meters away, that's RMS. So if that's 300 watts, then in reality, I need 900 watts in order to be able to pull it off. Because I need 6 dB of headroom built into the system in order to accomplish that from a perception point of view. Right? So suddenly that 300 watt amplifier now needs to be a 900 watt amplifier in order to account for the crest factor. Okay? That's it. So you now should have everything you need to know to do the rest of the homework. What we'll do on Monday is we'll talk a little bit about more about dB SPL and how exposure to that can affect your hearing over time, because that's a super important thing. So we'll learn about what that means, how to protect yourself, and then hopefully, if on Friday we can all do hearing tests. We'll go up to Pierce Building, and I have the booth and the little machine, and we can all give ourselves baseline hearing tests. So you know where you are right now, and then you have something to compare that against a year or two from now after you've listened to lots of loud sounds again, and you can see what sort of damage you're causing. Okay, that's it.